Hello. In this video, we will cover section 3.1, which is on the mean and standard deviation. In the last chapter, we discussed the ideas of center as the typical value and spread as variability of a distribution. In both cases, the ideas were treated informally and subjectively, which means that two people could look at a distribution and come up with different estimates for the two values. In this chapter, we come up with precise ways to calculate these values depending on the context. One way of measuring the center is as the balancing point of the data. This is the point where the distance between the data points in the center is the same above and below the center. This is called the mean. It can be calculated using the arithmetic average of the data. When the distribution is symmetric, the mean matches with our concept of the typical value. That last point is really important. The mean only produces our concept of the typical value when the distribution is symmetric. In the image below, the mean is illustrated with a fulcrum. A fulcrum is the point on a seesaw where both sides would be balanced. That's why we call it the balancing point. So right here is the fulcrum. And the idea is that if you take the distance between each of these points and the fulcrum, and the distance between each of these points and the fulcrum, you get the same value. So it's the same value to the left as to the right, or the same value below as above. Okay, so one way to think about that is that the points pull the mean in their direction. The further from the mean, the stronger the pull. The mean is located where the pull on each side is balanced. That's actually how I think about it, is I think about it kind of like it's a tug of war, and you've got points on this side that are pulling this way, and points on this side that are pulling, points on the left are pulling to the left, points on the right are pulling to the right. And you're trying to find the place where the pull on both sides, the tug of war would be balanced. And the points that are the furthest from the center exert the strongest pull because, again, what the mean is it's the sum of the distances between the points and the fulcrum. So these points are very far from the fulcrum, so they are going to exert a lot of influence. Same for these points on the far right. When the data is roughly symmetric, the balancing point is roughly in the center, which aligns with our idea of the typical value. However, when the data is not symmetric, the balancing point will be off-center, which may not match with our intuition of the center or the typical value. So the mean is less effective in that situation. So let's look at an example here to illustrate that. All right, so what we have is we have some data. The data are the winnings of the top 100 ranked tennis players. All right, so that's the distribution here. And then we went through and we calculated the mean. So the mean is at $1.8 million. So that's right here. That's where, again, the fulcrum. So there's the mean. And the issue with that, though, is that we have the information that 75% of the players make less than that amount. So if you've got 100 players that you've gone through and that represents your data here, and 75% make less than the mean, how can something that's less than 75%, how can that represent the center or the typical value? And the answer is that it doesn't. The mean does not work very well when it comes to skewed distributions, which is what we have here. The issue with a skewed distribution is that the mean is going to be off center. It's going to be off to one side, right? The tail here that we have on the right side of the skewed distribution pulls the mean off center, off away from the highest concentration of the data, and that ends up producing this outcome. So this is typical. When you have a skewed distribution, the tail is going to pull the mean off center, and it's going to make it so that the mean is not at the center of the data. It's not toward what we would think of as the typical value. And so the mean just doesn't work very well in this situation, if that's what your goal is to find the typical value. All right, so let's look at another distribution here, and we want to go through and practice estimating the mean. Okay, so the idea is you want to look at this, you want to try and figure out, all right, well, what's the balancing point? What's pulling, what's pulling what which way? All right, and so if you kind of think about this, it's pretty symmetric here. These middle, I would say 7 bars are pretty symmetric. And that would imply that the mean is going to be, maybe roughly in this middle bar here. The thing that makes it a little bit less symmetric is the fact that this bar is taller than this one. So that if it was just for those middle 7, I would say the mean would maybe be on the right side of this center bar. However, we have this bar here that's on the far left that is going to pull the mean and have quite a strong influence. Bars that are far from the center have a strong influence on the mean, and so it's going to pull the mean back to the left. And so from the right side, because of these two, it looks like we'd end up with something that's maybe on the left side of this center bar. Okay, so I typed up a lot of those thoughts here, so it's roughly symmetric. It isn't perfect. The bar right of the middle, that's this one, is taller than the bar left of the middle, that's this one, that pulls the mean to the right. However, the bar on the far left, that's this one, pulls the mean to the left. And then if you actually go through and calculate the mean itself, we get 467, which is roughly where this fulcrum is. And it did end up on the left side of this middle bar. Let's look at a homework example. So below we have a homework example. So it says the histogram below shows the number of televisions in the homes of 90 community college students. Judging from the histogram, what is the approximate mean number of televisions in the homes? So again, same idea. It wants us to kind of eyeball the distribution here and make an estimate. So if you look at it, it looks like the middle 6 bars are pretty symmetric. Okay, you can see this one on the far left and this one are roughly the same height. This one and this one are roughly the same height. There's a little bit of a difference here at the very center, but it's still not terribly far apart. And so if you were to ask me what's the mean with just that and excluding everything else, just those middle 6, I would say that this tall bar here on the left, I guess each of these bars on the left is a little bit taller than its equivalent on the right. And so that would pull it slightly to the left, and it'd be maybe right around there. However, that is not all the data. We have this bar here that's going to pull it a little bit further to the left. But then most importantly, we have this bar over here that's on the far right. And so this bar on the far right is going to, because it's so far from the center, it's going to exert a pretty strong influence. It's going to pull the mean over to the right. And so that, to me, that would suggest that the balancing point is probably, instead of being on the right side of this middle, the bar, the tallest bar, instead of being on the right side of that, I would say it's going to be on the left side of this bar to the right of that, the left side of the second tallest bar. All right, and so if it's on the left side of the second tallest bar, it looks like it's maybe somewhere slightly below 4, right? So we can see here that we've got 4 right there, and it looks like it's to the left of that. So it looks like it's slightly to the left of 4. All right, and so here I typed up all that stuff. Small amount of the bar centered at 2.5. That's the tall one, is taller than the bar centered at 3.5. That's the one next to it. It's going to pull the mean to the left. And then that's more than made up for by the bar that's way over here off to the right, that's centered at 8.5. And so in the end, we're going to end up getting that the mean is between 3 and 4. So the reason that I ended up using this language is because that's what the homework asks you to do. So it says, is the mean between 1 and 2, between 2 and 3, between 3 and 4, or between 4 and 5? And so we don't need to be any more specific than that. It looks like it's between 3 and 4 based upon the analysis that we just did. Okay, so calculating the mean. So there is a formula for the mean, and it's presented there. So let's kind of just go through some of the aspects of the formula. So there's this symbol, that's the Greek capital sigma. So that's the symbol that's right here. What that stands for is summation. All right, so this is telling us to go through and sum. And then it's telling us to sum this thing that's next to it. The X represents a single observation. So this is saying to sum the observations. And then when you're done, we want to divide by n. What is n? N is the number of observations. So we're going to sum the observations and then divide by how many there are. That is the arithmetic mean. And then we're going to say that the result of that is this X with a bar over it. That's the symbol that we use for the mean. And so you put it all together, the mean equals the sum of the observations over the number of observations. Let's look at an example going through and calculating the mean. According to gasbuddy.com, the price of 1 gallon of regular gas at 12 service stations in downtown, that's supposed to be Austin, are listed below. This was a different era in terms of gas prices than today. So we've got 12 gas prices, and that wants us to go through and calculate the mean. So to do that, we add up the observations. That's the sum part. So we sum the observations and then divide by the number of observations, and that gets us the mean. Okay, so let's change gears here and look at variation or spread. Previously, we talked about the idea of variation or spread. That was in a previous chapter. So we can see that illustrated below in the temperature graphs of two cities. So both are roughly symmetric, both have similar centers, but the data is far more spread out in Provo than it is in San Francisco. So the data is kind of highly concentrated in a narrow distribution for San Francisco, and it's very non-concentrated, very spread out in Provo. So what we introduce the idea of standard deviation. Standard deviation measures how far away the typical observation is from the center or the mean. Distributions that are tall and narrow, like San Francisco, have small standard deviations because a significant portion of the observations are close to the mean. So a tall, narrow distribution is going to have a small standard deviation because a lot of the observations are close to the mean. Distributions that are short and wide, like Provo, will have large standard deviations because a significant portion of the observations are far from the mean. All right, so let's explore this idea more. So consider the three graphs below. Intuitively, which has the largest standard deviation, which has the smallest, and why? And to answer this, we want to consider how far observations are from the center. So we've got our three graphs here. So here's the center here. How far are observations from the center in this case? We have the center, it's right about here. How far are observations from the center in that case? And then here, how far are observations from the center? All right, so think about that for a second. Which one do you think has the observations that are the furthest from the center? Which one has the observations that are closest to the center, based upon the shapes? All right, now you've had a chance to think about it. Let's actually go through and answer that. So distribution A has the largest standard deviation. The reason is that it has the largest number of observations far from the center. So here's our center, and we have a lot of observations that are way out at the far exterior of the distribution. So with a lot of observations far from the center, that's going to give you a large standard deviation. Okay, so if the typical observation is close to the center, then that's a small standard deviation. If the typical observation is far from the center, then that is a large standard deviation. So that's the idea. And then based upon that, we can see that distribution C has the smallest standard deviation because the observations are clustered very close to the center and tail off as you move away from the center. All right, so the bars at the outer edges are short. All right, so that means there are very few observations that are far from the center, and the bars at the center are very tall. So one thing that may have misled you, if you struggled with that, is to notice that the vertical axes are not the same here. If you were to put these on the same axis, these center bars would be very tall on this picture. So looks like the vertical height is around 325. You see the vertical height is 250 here. So if you went ahead and tried to trace this shape onto this graph, it would have looked something like this. It would have been very tall, with the observations all clustered around the center. The standard deviation doesn't have the equivalent of the balancing point concept to explain the mean, which is unfortunate. It doesn't have that. However, assuming a distribution is unimodal and symmetric, then the majority of the observations, roughly 2/3, are usually within one standard deviation of the mean. All right, so that is the way in which we try and wrap our heads around the concept of it, is by using an aspect or a feature of the standard deviation result. And that is that if you go through and calculate the standard deviation for a unimodal symmetric distribution, and you go through and, once you've got the standard deviation, if you add it to the mean to get one standard deviation above the mean, and you subtract it from the mean to get one standard deviation below, that region is going to contain 2/3 of the data that's within the distribution, typically. Okay, so we can go through and look at that in the cases we just discussed. So the standard deviation for San Francisco is roughly 8, and the mean is 65. So if you go on to this is San Francisco here, it is unimodal and symmetric, which is what we said were the requirements. If you go through and find one standard deviation below the mean, so to get that, you would take the mean and you'd subtract standard deviation one time. That gets us 57. And then if you go through and do the same thing, but you add the standard deviation, so we take the mean and add the standard deviation, that gets us one standard deviation above the mean. So now we have from one standard deviation below to one standard deviation above. That gives us a region on the graph, all right, a region. So if you go through and say 57, that's going to be right around here. 73, that's going to be right around here. So basically it contains the data that's in these middle 3 bars would be the data that's within one standard deviation of the mean. Now, if you go through and estimate how tall these bars are and go through and count up how many observations fit into those bars, which I went ahead and did, but I didn't have room to put the math on here. You do get about 2/3 of the observations that these 3 bars that are in the center, this 1, 2, and 3, those 3 together, compared to the total number of observations in the entire data set, those are about 2/3. Okay, so let's look at an example of standard deviation. So we have the mean in the distribution below is 7.9. So what is this distribution? This is the level of particulate matter for 371 US cities in 2017. All right, so someone went through, they measured the particulate matter in 317 cities, and then they put that data into a distribution, and this is what it looks like. All right, so we're told that the mean is 7.9. The standard deviation is 2.2, and we're asked to go through and find the level 1 standard deviation above and 1 standard deviation below the mean. And then we're told if 15 is the safety limit, all right, so you want to be below 15. If you're above 15, then it's unsafe. Then what can we say about most of the cities in the distribution using our standard deviation result? All right, so let's go through and take a look at that. So to find 1 standard deviation above the mean, we take the mean and add the standard deviation. So that's 7.9 plus 2.2, that gets us 10.1. And then to find 1 standard deviation below the mean, we want to subtract the standard deviation from the mean. So we take the mean and subtract the standard deviation. That gets us 5.7. And then as far as the 15, notice that 10.1 is less than 15. So 15 is above the upper band of above the upper standard deviation, the upper 1 standard deviation. And so if 1 standard deviation contains 2/3 of the data, and the upper bound of 1 standard deviation is below 15, then we know that 2/3 of the data is below 15. So that suggests that most cities are below the limit. And actually, if you look, and that's without even looking at the graph. If you actually look at the graph, you can go through and you can see 15. You can see, okay, well, there's only a tiny number of cities. But you could do that assessment, what I just did. You can do that without even seeing the graph. You can go through and find if the upper 1 standard deviation is at 10.1, and you're comparing that to 15, then you know that 2/3 of the data is going to be below the upper 1 standard deviation. And so that means that 2/3 of the data is going to be below this 15 threshold. Okay, hopefully that made sense. All right, so how do you calculate the standard deviation? The formula is a little bit complicated, but what I recommend you do is you break it down into steps. So what you do is you take the observations and you subtract the mean from them. You want to do that for all of the observations. So you go through each one. So take an observation, subtract the mean, go to the next observation, subtract the mean again. Oops. Sorry about that. And then you just go through and do that for all the observations. When you're done with that, you go through and you square each of those results. That's what this square represents. So you want to go through and square each of those results. And then after that, you want to go through and add them up. So after that, you want to add up the results. And don't worry, I'll show an example of this in a minute. You want to go through and add up the results. And then once you've added up all those results, you're then going to divide by the number of observations minus 1. And then you're going to take the square root. And that's what all this stuff says below. First, subtract the mean from each observation. Then when done, square the results. Then go through and sum the results. Then divide by the number of observations, and then take the square root. All right, so let's see an example with that. Hopefully we'll illustrate this more clearly. All right, so first here we have all 12 observations from the gasbuddy.com problem. So first you go through and you subtract the mean from each one. All right, so you want to go through and take 219, subtract the mean. 219 again, subtract the mean. 239, subtract the mean. Do that for all the observations. When you're done with that, then go through and square each of those results. So we take this result, square it, this result, square it. Do that for all the results. And then you're going to go through and add all those up. So sum all of those, and that gets us this number 0.061. And then once you've done that, you want to divide by the number of observations minus 1. So there are 12 observations. So 12 minus 1 would be 11. And then when you're done with that, you're going to go through and do the square root. And so you can kind of see it all written here together. So the sum of the observations minus the mean squared, that gets us the 0.061, right? So that's the sum of these. Then divide by 11, that gets you this, and then take the square root. Okay, and then so another way of going through and measuring variation or spread is called the variance. So the variance is the square of the standard deviation, or you could think of it as the standard deviation formula without that last square root step, right? So if you kind of go through and compare this formula here with the formula here, they are the same except without the square root. Okay, the variance serves a similar purpose. It also goes through and measures the variation or the spread. However, you very, very rarely see the variance. The standard deviation is a far more popular way of going through and measuring the variation or the spread. So I'm just covering it here for completeness because it might come up on the homework, or later on you might encounter it. And so variance is something that does exist. It is a way to go through and measure variance or the spread of the data. However, it's very unpopular. Okay, so that is the video. Thank you for watching, and I'll see you next time.